This test, what sections?
4, 5, 6.
Yeah, chapter 4 through 7, 11. Chapter 3 had its own thing. It had its own special day off. 4, 5, 6, 7. So, the very first chapter starts with that x, p of x business. Oh man, now I gotta make it really clean. Can't stop. Just stop. So we got this hopefully very familiar formula there. And this, hopefully, I could write this a few different ways. I don't know what's going to be best for you, but maybe this will. Right? So we talked about why those formulas made sense. We derived them. We even used some algebra on that second one to make it work. Right? But now it's just the formula. The formula tells you when to use it. When do I use these formulas? Probably when I give you a bunch of x's and p of x's. Yes, maybe? Yeah. Okay. I like it. And then we also had this little dude. And these little dudes. And this was all from section 4.3. This, of course, dealt with what kind of distribution? Nope. Nope. Binomial. There you go. I like it. Just start listing off everything we talk about. Binomial is what I call an NPQ problem. P and Q, two outcomes. That's where the word binomial comes from. Two possible outcomes. Okay. So that's chapter 4. Let's see if you're one. Yeah. Stay with me. Chapter 5, there's no formulas. Chapter 5 was about continuous distribution, uniform distribution. Now, let me say this. I'm just going to say it, you guys never understand. There's a homework problem about the mean and standard deviation for a uniform distribution. If you've done that problem, you had to look up the formulas. It was a plus b over 2, b minus a squared over 12 square root. Does that sound at all familiar to anybody? If it doesn't sound familiar, then you better step up your homework game. Holy shit. So you had to look them up and throw shit into the formulas. Okay, I want you to realize, what did I promise you about every time we learn a new distribution, a new way to get data, there has to be another mean formula and a standard deviation formula, because those are the two most important things. So we have a uniform. I want you to realize those exist. I want you to get a little practice putting stuff into them, but I'm not going to put a question about them on the test. And the minute I say that in your brain, you're like, well, why the shit did you make me do anything? Well, because, there's more to everything besides tests. All right? Yes?
So if you ask us one religious Latin test, would you notes rather than
All right. So we never calculated the mean and standard deviation of a uniform distribution in class together. It was a problem in the homework. What do we do? What kind of problem about uniform will you have? Drawing them, figuring out the height, probability questions, right? So we're going to do those level of problems. But I did assign some homework questions, and I did have actually one question on the practice test related to the mean and standard deviation of a uniform distribution. We'll see. Anybody still listening? When we get to number 6 on the practice test, I will explain to you why I put it on there, because it does illustrate a bigger idea that will be on the test, for damn sure. Okay, I like it. Sure. I got multiple paparazzis. It's on there too, man. Well, you can get it too, it's fine. I'll take that top picture. All right, good. So, chapter 5, nothing to write down. You have to know how to make the distribution picture, the big rectangle, and then you have to know how to calculate probabilities. That's all you got to know in chapter 5. Chapter 6 brought this back. And then it had the little reverse dude for that. Cool. So those are the two main things from chapter 6. The other part of it was knowing how to use the chart correctly, knowing how to go both ways and all that kind of stuff. Yeah. And then chapter 7 comes along and says, do this sometimes. Now, if you want to, I think I said this before, I have a claim that the z-score formula never changes. And as we write down z-score formulas with different letters in them and stuff, you will start to look at me more and more like I'm crazy. But the z-score formula is always my data point minus the middle, my data point minus the middle divided by the spread. That's what it always is. Because the idea of a z-score doesn't change. That's why I'm going to ask you that question on the test, right? What does a z-score tell you? What does it tell you? What's it going? Number of standard deviations from the mean to the data point, or the number of standard deviations that a data point is away from the mean. There's all different ways to say that sentence and have it still make sense. I like it. If you just throw the right words on the paper in some kind of weird order, you're not going to get points. There's an idea there. So sure, you can memorize the phrase, but it'd be better if you just saw what the idea was. Okay, maybe. So again, standard deviations are like tick marks on a ruler. The z-score is putting the ruler down and saying it's 5 inches away. So a z of 5 would actually mean it was 5 standard deviations. And you can tell me right now, is that far? If somebody's height was 5, a z-score of 5, that would mean that they are really crazy tall, right? They are 5 steps above the average. And where do things get unusual? Just 2 steps away. So 3, yeah, you're right. It is really freaking unusual. So 5 is like, okay, Guinness Book of World Records. Come out here right now. Right? Maybe. And it's okay because he can't hear you. All right.
Either you asking the question that what is standard deviation mean? What is this one? So
I could ask either one, but I definitely will ask. I will ask this question one of 2 ways. I will ask it, what does a z-score tell you? Number of standard deviation from the mean to the data point. Or I'll say, what would a z-score of 2.03 mean about a data point? Then you better be a little more specific. What would it mean if the z-score was 2.03? That data point is 2.03 standard deviations away from the mean or above the mean because it's positive. It's either way is fine. Okay, so someday I'll get more than half of everybody get that one right. I don't think I've quite gotten there yet. I know. So everybody's like, just tell me what's on the test. I do. I don't understand. Oh shit. All right. You could now. You don't have to write this next formula down, but you could if you wanted to, right? But look how disgusting that looks. Doesn't it look disgusting? Does everybody see how that's the same formula as this one? So what do we do when we have a central limit theorem problem? We change the standard deviation and we put that here instead. That's basically what this thing is saying. So if you don't want to write this down, don't. You don't need to. It's still just that formula. Okay, I like it. All right. So we can go a few different ways with this. So I want to do at least a few things off of this sheet. I don't think we actually finished any of these problems together yet, right? We got to B on number 1? Or B on number 2? B on number 1, okay. So let's do that real quick. I don't have to do all of these. I'm going to let you guys do a couple, and we can do them later if you want, if anybody wants to see them. But I just want to remind you guys, especially if you just got this today, this is exactly the way I love to set up a problem, is either number 1 or number 2. I could do it either way. What is the difference between number 1 and number 2? And from a statistics standpoint, what is it? What kind of distribution is kind of the best? It's not the best one, but what would it be nice if it was distributed normally, because then I have a whole sheet of answers, right? I don't really have work to do. I just have to go look up answers. Okay. So we did that first problem, I guess. Yeah, Jeff, that's what they said, man. Good job. Good job. So here, just to remind you guys, so we had this. Why am I allowed to do either of these, actually? Because if I don't, what is it that I tell you? I tell you that it is normal. I like it. Number 2, I don't say that, do I? I don't say anywhere in here that is normally distributed. But what saves me immediately, sample is 37, which is bigger than 30. So central limit theorem says the mean stays the same, the standard deviation changes, and if the sample is bigger than 30, the sample means will be normally distributed enough. Yes?
Is that all we have to write to get a point?
Yeah. I mean, you could write more, but to be honest, that's it. Because you've shown me what you're comparing it to. You've shown me that you know what to look for, and you could say central limit theorem says it's okay, but I'm not as big on names as I am in concepts. So if you forget that it's chicken, lettuce, tomato, then that doesn't matter. So this one we already did, but just a real quick. I know it's normal, so I can draw this picture. Jeff, it never looks good when you look down. What goes in the middle? 2.9, because it's a mean. I like it. And then I want more than 3. So this is your classic z-score problem. I have x's, I know it's normal. If I make it into a z-score, I can look it up. So we did this last time, 3 minus 2.9 divided by the spread to make it into a z-score. Don't remember what that was. 0.32? 0.29? 0.32? Sweet. Sometimes my memory works. And then who knows what we got? We looked up 0.32 and we got 6255, and then we did 1 minus that to get 0.3745. So about 37.5% almost chance that a woman would have a bone density greater than 3. She's got some Wolverine bones going on, right? And then maybe not quite, it's not that far away, but yes, no, maybe so. Or you could say about 37.5% of all women have a bone mineral density greater than 3 grams per square centimeter. Okay. Whew. So as you get older, you want to have that checked out. Calcium leaches out, you become all brittle. Oh shit. Something to look forward to, kids. If we pick a sample of 22 women, what should I do immediately? Standard deviation's got to change. So how do I know when to do this? That is the most common question across all math courses I've ever taught. Is all right, I understand that, but how do I know when to do this? This tells you. It's when I take a sample and I ask a question about the sample mean. That's what's happening. I took a sample of 22 and my question is about the sample mean. Do you guys see that? So I talked a lot about the idea behind central limit theorem. We did Florida shit, we did numbers out of a hat, we did all this crazy stuff. But at the end of the day, that's all it is. There's a trigger now. How do I know to do this one little thing when those two things happen? Took a sample, asked about the sample mean. So the very first thing I should do is change this. What am I going to divide by? The old standard deviation divided by the square root of 22, because that's the sample size. If you put a decimal in there, that makes no sense. Go find 5.7 people. And then I'll let you put a decimal in there. Maybe don't, because that's scaring me. Some of you guys, I don't know. Alright. Tell me, what do you get there? 0.66, or you can even go further. I like it. And now, you just do this whole thing, the same work, because it is sort of the same problem. You see that? Greater than 3. It's the same problem, but instead of using 0.31, I'm going to use 0.0661. So right here, it's going to be the same picture. It's going to be the same z-score formula. But right here, what do I put there? Yeah, I put the correct spread. So just remind you guys, this standard deviation is good for individual women. That's good for individual women. That's why it worked when I just took one woman. Because then I can compare to all other individual women using this spread. Part B, I'm talking about a frickin' group. I want to know how spread out all the groups are from each other. I've got to change that. Okay. And then whatever you do. Yes?
I have a more general question. So, for like X, how many like decimal points do you usually want us to round to?
For X.
Like if we were to calculate, for example, that X, or like X bar.
Oh. So either I'll say in the problem, but if I don't say, I would go a couple places, just to be safe. But if I don't say, just don't round to a whole number. I almost never round to a whole number, right? Okay. Yes?
So we know to use that top equation when you're asking for the sample mean.
When the question asks about the sample mean. So if I did take a group of 22 women, what's the probability that those 22 women had a mean bone density of more than 3? Should that be more or less likely? If you go find one woman, her bone density being greater than 3 is something, right? The mean is 2.9, so it should be close to 2.9. If I take a group of 22 women, should it be really likely that their average is above 3, considering the average for everybody is 2.9? No, it shouldn't be very likely, right? So I already know this probability should be smaller than the one I got in the first place. Do you have to know that ahead of time? No, you're going to look it up and get the number. Okay, so anybody get that z-score yet?
1.52.
1.5? 1? Okay, I don't know. I'm just crowdsourcing this question. Alright, and then you look it up. I'm going to get the wrong answer, but then I'm going to get the right answer, right? There's a little bit of confusion about, the z-score chart is incredibly single-minded. It's a piece of paper. So it can only tell me the area below what I looked up. It doesn't matter to me it matters what the question is, but the piece of paper don't know what the question is. It was designed just to tell me area below. I don't want area below, so then I adjust what it tells me. So when I look up 1.51, what do you guys get? 9345. Where do I put that? Yes. I like it. But nobody was like, I'll tell you where to put it, Jeff. And of course, that's not the answer yet, because I was nice to myself and I shaded in the answer. So what's the actual answer? Yeah, 1 minus that, so it'll be 0.0655. So it went from a 37.5% chance that one woman had a really cool bone density to only a 6.5% chance that a group of 22 women. And that only makes sense. It should be harder for a whole group to get that far away from the average than just one person. No. Okay. And then real quick, down here, so we got part A answered. This is part of the central limit theorem, so if I'm probably going to ask a question very similar to this. Okay. So you're going to have to tell me the sample size is big enough, right? Why didn't it matter? Why is this okay that this is only 22? Huh? What the shit? That's less than 30. What? Why is that okay on the first problem? Because I already told you it was normal. I don't need the sample size to save my ass. If I don't say it's normal, I can't do shit unless I took a sample bigger than 30. Then the means will become normal enough. Okay. But if I say it's normal, hey, I can do whatever the hell sample size I want to. It's already normal. So what's the very first thing I want to do in part B? Sure, I like, you can draw a picture. What goes in the middle? 80.2. And then I'm curious about 75, right? We want this person to die early because we're evil. So nobody in here, I don't think, was born in 2004 in California, but if you know somebody that was, then this is true. I actually looked this stuff up and give you a couple of sources so you can go double check me if you want to. But somebody born in California in 2004 was expected to live to 80.2. Do you know that across the recession that number went down? 2006, 7, 8, we lost ground. The life expectancy for the United States went down. Yay, go team! Jeff, you're laughing. Yeah, what the hell can you do besides laugh? But now we're hopefully going back up in spite of. Anyway, doesn't matter. Continuing on, what do I need to do now? So drawing a picture, you're right. It could always be your first step. But what's my, before I do any calculations, the very first thing I got to do? Standard deviation has to change. Why? Took a sample, and I'm asking about the sample mean. So the number that works for how spread out individuals are will not do shit for me on this. I need to know how spread out groups of size 37 are. That will be applicable because that's what I'm talking about. I really want that to make more intuitive sense as to why this step has to happen. That sigma is for individuals. I need the one for groups of 37. So I do this business. You do it over here. What is it? 14.9 is what it was for an individual. Divide by square root of 37 because that's my sample size. Kick ass, and then whatever the shit that is. All right, Jeff, man, you don't have to cuss so much. Shut the hell up. What do you guys get for that? 2.45.
Oh, it's 449.
Oh, okay. 2.449, blah, blah, blah. Okay.
I don't know what.
2.450, is that look good?
Yeah.
Okay. Not that I don't trust you. And then the work doesn't, once I do that little modification, the rest of it is the same as always. Make 75 into a z-score using that spread, look it up. The beautiful thing is this is an area below, so I don't have to do any 1 minus shit, right? For stuff. I love it when people bring their kids to my class. It's such a great. I'm like, holy shit, people German? Z equals, what would I put this? 75 minus 80.2 divided by 2.45. I got to use the spread that works for groups because this question is about a group. I think it's like 2.6 maybe. I don't know. Negative 2 point 1.2. Yep. Man, that was off. Negative 2.12, and then you look that up and you're done. Because the question wants the area below. 2.12. What do you guys get? 0.0170. So less than 2% chance that a random group of 37 infants born in 2004, I should have said, will die before they reach age 75. What a happy question. Well, it's nice. Less than 2% chance that their average age of death would be less than 75 years. I like it. Okay. Now, we were born before 2004, so we're dying earlier. So, yeah. Too bad for us. All right. I think you can do the other two if you want to and ask me about it, but I want to open it up to whatever you guys want to look at. Yes?
So, like the question is, would it be unusual to find blah 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 between the
Yes, good. So if I ask you, would it be unusual to find 11 people that do something? That would be in that binomial problem, right? More than likely. Because how do you find the max and min usual?
Yeah.
Well, we said this earlier. Where does unusual start? Say it. How many? 2. Okay. So if I know the mean and I go up and down 2 steps, that's where the min and max usual is. So for example, if I flipped a coin 100 times, would it be unusual to get 40 tails? This is not a subjective question. This is not a, how do you feel about this? This is a technically defined idea of unusual. I love you guys. So what do I need to figure out then? Probably that thing and that thing. How do I figure out the mean for an NDQ problem? What's the beautiful little formula for the mean? N times P. So it'd be 100 times 0.5, which is 2. So I know where the center is, and then I want to know what the spread is. So then I'll know what 2 steps away is total. So the spread is a little bit freakier equation, but still NPQ square root. And that's going to be 5. Well, I picked a good number. Holy shit. Right? Isn't that 5? Somebody do that for me? Half of 100 is 50, half of 50 is 25. Square root of 25 is freaking 5. That's beautiful. We're going to have to do some weird shit for that one. Now don't worry, we know how this problem would go. I would ask you to calculate the mean. I would ask you to calculate the standard deviation. And then I would say this, would it be unusual? And then you just figure out, well, where's unusual start? So if you wanted to, you can do it visually. Put the mean in the middle. If I go up a couple steps, where am I? Go up 60. Go down a couple steps, where am I? 40. So that is right on the edge. I like it. Semi-officially, there is a soft parenthesis there, meaning that 40 would be unusual, but I probably wouldn't ask you a question where it's right on the edge. So 39 would officially be an unusual number of tails. 41 would not be. So officially, 39 would mean, did somebody do something to this coin? You guys with me? No. You guys are with me at all? Today's weird. Yes.
So at 2 standard deviations, things start to get unusual.
Yes.
So is it like exactly 2 standard deviations?
Yeah.
It's anything outside of 2 standard deviations away.
So would 40 be unusual?
40, we could say it won't be unusual. Officially, it's sort of a soft parenthesis there, but 40, if I did ask you that, you could say no. It's the minimum I would expect to see. So if it's outside of there, then it would be unusual. So I would ask you a question like 37. Would that be unusual? Yes. So that would be, you've all seen, and remember this, did I give you the example of the nuclear power plant yet? Where I don't want to always have 2 standard deviations mean unusual. If things are getting weird in the nuclear power plant and they're like maybe 1 z-score away from normal, am I not going to get off my ass and go see what's happening? I'm not going to wait for that little needle. So have you ever wondered how do they make that needle that has green, yellow, red? This. They can define where warning starts and where danger starts by the number of standard deviations away. So you're going to be a little more careful in certain situations. So it's not later this semester, it's not always going to be 2. If it's a nuclear power plant, I might make it 1. Because once you're outside of 1 step away, I'm going to get on top of that shit. Because you never know, it's going to go, oh, that's okay. But, oh, I should have done something. No, yes, maybe. And then other situations that no one's going to die. Who gives a shit, Oh, it's 3 standard deviations away. Maybe I'll look at it tomorrow. So something that's not a nuclear power plant. Okay, so later we'll make 2 a little more flexible depending on how bad it would be if it really was out of whack that much. Okay. I don't know if it really answered your question. Yes. Kind of? I did. Okay.
Just for review, can you go over a problem with the uniform probability where you draw the...
Oh yeah. And real quick, did you have a question about what we're talking about now, or?
Yeah, so if it was like 98, you say usually because it's not used.
Yeah, it's not in the usual area. It's outside of what I would expect to happen.
So that would be like a good explanation.
Yeah. In fact, if I ask you this question and you draw this picture, and I ask you is 38 unusual, you just put it right there and say, yeah, it's outside of this. Yeah, outside of that. And Jeff will go, sweet. Because that's the purpose of drawing this. You can reference it very quickly then. This is the definition of usual. That's obviously unusual because you were nice to yourself and drew a picture.
So on the scale, there's nothing to do with the means and the maximum. Just subtract 1.
Well, this is the minimum and the maximum expected, the usual, right?
After we file it, we put the min and the maximum.
Yeah, how did I get this number? I went 2 steps down. So that is the minimum usual value, and that's the maximum usual value.
One of the paper you gave us, there was like, you subtract 1 standard deviation and you add in 1 standard deviation. And another paper, you said that.
Listen, so if I say what percentage of the data is within 1 standard deviation, that's very direct, only 1 step. What's the definition of unusual? 2 steps, right? So if I said, what percentage of the data is within 3 standard deviations? You would go 3 steps and you'd look to see what percentage, right? But if I say, is this unusual, you better go out 2 steps because that's what unusual means. I can pick any number I want to make you do it.